Hey everyone, so today we're going to go over normal force like on inclines and how that may be different from normal force on a flat surface. So once again, normal force is simply just perpendicular to the surface. All right, it's always perpendicular to the surface. It's a force that's acting perpendicular to the surface. So if we have an incline and say that incline, it has an angle, which is theta, and then we have a box on it. The normal force is going to be perpendicular to the surface. You're going to have your weight force or your force of gravity acting that way. And then let's say it's sliding down the incline. So we're going to have our F net. And so I'm not going to go over how this is because most of you won't be on the hook for it. But your normal force in this case is going to be equal to mg cosine theta. So if you have theta and you have the mass, you can calculate the normal force. And then your net force, which is the way it's moving, is going to be equal to mg sine theta. So if you have your angle and you have your mass, you can calculate the net force too. And just as a little side note, as theta goes up, the normal force is going to go down. And obviously, as theta goes down, the normal force is going to go up. Not too complicated. Now let's try a different example or a different concept. Let's say we have a frictionless surface. So we're going to go no friction. We have a box on the frictionless surface. And we have our Fx, which is just going to be, we're going to have Fx be the movement instead of F net, Fx. And then we have our F net. If someone was trying to calculate the acceleration of the box on this ramp, how would they do that? Well, we would start with Fx is equal to F net. And as we said earlier, F net is equal to mg sine theta. And then Fx, which is technically F net, but just for making it for simplifying this, we're going to keep it Fx, is equal, any force is equal to mass times acceleration. So mass times acceleration is equal to mg sine theta. The two masses cancel out, so acceleration is equal to g sine theta. So if you have the angle of this ramp, you can calculate the acceleration because we don't need mass. Let's try a different example. But once again, this example is completely dependent on the angle. Let's try a different example. Let's say this time we have friction. It's no longer a frictionless ramp. Let's say we have a ramp, and on this ramp, we have a box, and it has a net force. Let me redraw that, make it nicer. It has a force of friction, but the Fx, the overall direction, is moving down the ramp. How would we calculate acceleration here? All right, well, before we can do that, it's important to know that Fk, the friction constant, is equal to mu k Fn. All right, so now that we have that off to the side, we can go Fx is equal to F net, since they're both going in the same direction, plus negative Ff, the force of friction. And then we can do mass times acceleration is equal to F net, which we said earlier is mg sine theta, and adding a negative is the same as subtracting a positive, so I'll just subtract, minus mu k Fn. And then now that we have this, we'll simply cancel out all the masses. Oh, sorry. We're not done yet. We can expand this out. We can go MA is equal to mg sine theta. And then we know that Fn is mg cosine theta. As we said earlier, Fn is equal to mg cosine theta. So here we'll go minus mu k, I apologize for the mess, mu k mg cosine theta. And then now we can simply cancel out all the masses. So cancel those two out, cancel this out. So acceleration here is going to be equal to g sine theta minus mu k g cosine theta. So we can see that if we have the angles once again, we can calculate the acceleration on a friction or frictionless ramp, regardless of what the mass is. And once we know these formulas, we can apply this for whether it's going down, going up, whether it's like staying still because the friction force is too high, if something is pulling it up, like we can calculate all of them. And I'll cover those in future videos. Thank you.